Hello, and in this video, in the start of the second chapter of Further Mechanics, we're going to be starting off by looking at something called work. Okay, and actually, before we do start, something to note for this chapter, we're going to be needing some stuff from normal maths on the mechanics side, even from year 13. So that'll be particularly relevant if perhaps you're doing this in year 12. Some people do further maths year 12. So what I will do in this video is, when relevant, I will go over very quickly just the stuff you need to know to approach this chapter. Okay, just the essentials. Okay, but even if you learnt it, it'll be a recap. Okay, so we'll look, so that's something to note. There is some prior knowledge. Okay, right, so work. So as you can see, I've got these two pictures on here. And so the idea of work, you can kind of think of it as a physical work, or working out, or movement, something like that, right? Then the idea of work, you can see with these two pictures, is we've got this, we've got a person that's pushing something forward, right? So whether it's pushing a boulder up a hill or pushing a crate, okay? Those are examples of work done. So the idea of work is, work tells us the energy we use to push an object forward. Okay, so you can imagine with the top example, the person pushing a heavy boulder up a hill is going to need a lot of work to move it forward. Okay, so they're going to need to use a lot of force within themselves to push it forward, right? Compared to the second example here, you can imagine it's going to be easier to move the crate forward, so less work is needed. So in other words, less energy the person needs to move it forward. Okay, so I'll summarize here. Work essentially tells us the energy needed to move an object forward, right? Okay, and so we're going to need to come up with some sort of formula. Well, obviously there's going to be two ingredients. Well, the first bit is obviously force, right? If an object is heavier, we're going to need more physical force to push it forward, but also we need to account for how long we're doing it. For example, say if we push the boulder up here for 10 seconds, compare that to, say, a minute. Well, obviously we're going to need a lot more energy to move it in a minute if we keep doing it for a minute compared to 10 seconds. So actually we can say that as a formula, we can say that the work is going to be equal to the force times the distance moved from the object. Okay, and so that's the key formula we're going to be working with. Okay, now as for units, well, force is going to be in newtons, distance in meters. So for the units for work, then, where you could deduce it's going to be newton meters if you literally multiply the units. But as I hinted here, it actually is involves energy, and it turns out, if you are quite clever with using other formulas, that actually we can also say the units are going to be in joules. Okay, and that's the common unit we use. So work is actually a form of energy. It's the energy we put onto an object to move it forward. Okay, and so that's essentially it. Okay, now we're going to be looking at our first set of examples. However, as I hinted, there is some prior knowledge we need before we step into this. So what we're going to look at first here. Okay, well, I've got a car on the on my screen here. So first, what I'm going to do is we need to just look at the actual forces acting on a car. Let's say the car is obviously moving forward. Well, firstly, you can see this force here. Now, if the car is moving forward, that means there's a driving force that moves it forward, okay? Driving force essentially means a forward force. So it's the force that literally moves you forward, okay? Now, again, as you can imagine, if you're on a road like this, there's then going to be friction that opposes it, okay? Or more generally, a resistance, okay? So so you can imagine the force is trying to stop a car moving forward, friction on the road, but also perhaps air resistance as well, right? So there we are. So those are what we call the horizontal forces. So that's the right and the left force, okay? So those are those forces. Now, actually, as well, you'd be aware that everything has a gravity that tries to pull it forward, right? Every object on the Earth has its gravity pulling it down. That is the weight, okay? The force that pulls you downwards due to gravity is your weight, okay? Now, then you can imagine, well, you're just going to sink through the road. So what keeps you up on the road? Okay, what stops the weight? And that is called a reaction force. Okay, so these are the four main forces we're going to be using extensively in this section here. So that's the forces. Hopefully happy with that. But of course we need to be more mathematical. And so there's a bunch of formulas we need to know. The first one being that the force, the friction force, I'll do it over here. So key formulas. Friction is actually equal to this mu, this letter mu, this funny u, times the reaction, okay? Or more simply, F equals mu R, okay? So what this is saying is friction is a multiple of a reaction. Now, now more specifically, this mu is what we call the coefficient of friction, okay? I'll make a note of it here. So what mu, coefficient of friction, well, it's usually between 0 and 1, okay? So it's kind of like probability. So mu basically tells me how sort of slippery the surface is, so how slippery the road is, right? So if mu is closer to 0, that means it's very slippery, so there's barely any friction, okay? But if mu is closer to 1, then that tells me it's very sort of sticky. The car will stick to the road essentially, a lot of friction. So you can imagine if it moves at 0, it's going to be icy, very slippy. But then if it's 1, it's going to be hot and sticky, okay? So actually that's a formula we can use to link the friction to the reaction, okay? The second formula is actually to do with the weight, okay? So we can actually say that weight is equal to the mass of the object, so the mass of the car, times g. Now g is just a number, it's a constant number like pi and stuff like that. Now g, we usually say g is 9.8, okay? So we can actually say that the weight, so we can say that W is equal to mass times 9.8 usually, okay? So that's, so there we are. So we can compute the weight using this formula as well. Now the last formula is going to be force equals mass times acceleration. Okay, so if the car in this example is moving forward, then there's going to be an acceleration there. Okay, so there we are. So acceleration tells me if something is speeding up or slowing down, by the way. Okay, now again, we can summarize that as F equals ma. Okay, so these are the three formulas you need to know before we go into this. Okay, now as a quick sort of numerical example to demonstrate this, let's say I have a car. I'll do it down here. 50 kilogram, 500 kilograms. Okay. I have my my weight W. So my weight. I have a reaction force. I have my friction. And I have my driving force. Okay. And also the acceleration in this case, I'm going to say is 10 meters per second squared. So that's the setup, right? And the idea is now I want to find all forces. Okay. Using these three formulas that I've boxed here. Okay. So firstly, I can compute the weight. Okay. So firstly, the weight. Well, as I said, that the weight, that's going to be mass times G. So G is 9.8. Okay, so well, the mass is 500, right? So that means the weight is 500 times 9.8, and so that will be, if we work out that, 4,900. Okay, and that being newtons because it's a force. So that means we can say that the weight now is 4,900. Hopefully we'll be there. So weight is mass times 9.8. Okay. Okay, so that's my weight then. Now I'm going to find the reaction force. I'm going to do that by now looking at this formula. Force is mass times acceleration, or F equals ma. Okay, well, what exactly do I mean by force? Because there's four of them here, right? Well, so what we can do is actually look at two different sort of directions. Okay, we can look horizontally, so the right and the left force. Then my driving force to the right and my friction to the left, or we could look up and down, so vertically, which is my reaction and my weight force. Okay. So what I'm going to first look at is up and down. So what I'm going to say is R, so resolve up and down like this. Okay. So I'm going to look at my upwards and downwards force. Right. Well, firstly, upwards is the reaction. Take away the downwards force, so the opposite force, which is 4,900. As we just worked out, that's the weight. That's going to equal mass times acceleration. Okay. Okay, right. Now, the math. So if I write this out again, reaction minus 4,900. Well, the mass is 500. And the acceleration now. Now, because we're looking vertically, you might think, well, I said the acceleration was 10, but look at the direction. The acceleration is horizontal. It's moving to the right. Okay. But this is different. We're looking at the up and down direction, the vertical direction. There is no acceleration upwards. Okay, 0. Okay, so that means vertically there is no vertical acceleration, because this again is a horizontal acceleration. Okay, it's moving right and left, so that means the vertical acceleration is 0. Okay, so that's the idea. We could split up to horizontally and vertically. Okay, but there's no acceleration vertically, so actually it turns out this all equals 0. Therefore, simply my reaction is also 4,900 newtons. So I can add that on. Right, what's next? I'm now going to find my friction force. Now that I'm going to use the final formula we haven't used. That's going to be the my friction is mu, so my coefficient of friction times reaction, or F equals mu r. I've not told you what it is. I'm going to say that mu is 0.5. So again, the coefficient of friction that tells me how slippery the road is 0.5. So again, friction is mu. Actually, what I'm going to friction is mu times the reaction, and I'm going to box. I'm going to box my solutions to make it clear to separate things. Okay, so that's my weight. That's my reaction. Okay, now looking at friction. So friction is mu times reaction, but I know my reaction, it's 4,900, and that mu is 0.5. So my friction is going to be 0.5 times 4,900. And so that will get me 2,450 newtons, and that is my friction. Okay. I can add that on then, my friction of 2,450. Right, the final force we need to find is the driving force, so the forward force, right? So to do that, well, we've looked at the we've looked at the vertical, the up and down forces. Now we need to look at the right and left forces, so the horizontal ones. So again, what I'm going to do now is now say resolve right and left like this. Okay, so my right force is again my driving force. Okay, then I'm going to take away the opposite, so that's going to be my friction force in the opposite direction, 2,450. And so that's going to equal mass times acceleration, right? MA. Well, my mass is 500. Now, the acceleration is going to be 10 here, because the acceleration is 10. That's horizontally, but we are looking at the horizontal forces, right? So actually, they set the horizontal acceleration, which is what we want here. So again, this is horizontal, so right and left. And then the one we looked at previously was vertical, so up and down. So the horizontal acceleration is indeed 10. And so therefore, we simplify this. The driving force, take away 2,450 equals 5,000. Okay. So therefore, we can then work out the driving force by adding this 2,450 on to be 7,450 newtons. And there we are. That is my final force. Okay, I can add that on. Okay. So that is just a breakdown of the key things you need to know before we go into this. So these 3 formulas here. Now hopefully this has shown you how we can use the formulas there. Okay. But again, hopefully you may have seen this already in normal maths. But there we are. We will be using these techniques. Okay. Right, now we're going to look at what we do need to know. What we were supposed to be looking at work. Okay, so we've got this first question here. I'm told a box is pulled 7 meters across a horizontal floor by horizontal force of 15 newtons. Calculate the work done by the force. Okay, well, work, as we've seen at the start, the work is the force times the distance moved, right? Well, actually, we want to find the work. We know the force is 15, and actually the distance is 7 meters. Well, actually, that's quite nice. We just use the formula to get the work to be 105 joules there. Okay, or Newton meters, right? Whatever units you prefer, but that's the number. Okay, 105 there for the work. Okay. Okay, so we've got this question here. So we're told a packing case is pulled across a horizontal floor by a horizontal rope. The case moves at a constant speed and there is a constant resistance to motion of R newtons. When the case has moved a distance of 12 meters, the work done is 96 joules. Calculate the magnitude, so the number or the size of the resistance. Okay, right, so this is a bit more wordy and a bit more weirder than the last example. So what we need to get into the habit of, if we haven't already, is to start to draw the situation out, because it will really help visualize the equations we need to do. Okay, so if we look at the first example very quickly, if we were to draw it out, okay, so a box is pulled 7 meters across a horizontal floor. So we've got a floor like this, okay, that's a horizontal floor. So we have a box, okay, and it's being pulled by a force of 15. So it's been pulled like this, the force 15. So the and then the distance is 7 meters. So that's the situation there. Okay, it might be quite simple, but that is the diagram there. Now, if we were to draw the diagram here, then, so again, I've got this packing case. So it's being pulled again on the floor. So again, we have our floor. This is my packing case. Again, I'm just going to draw a simple rectangle, a little box. No need to overcomplicate it. This is my case. And it's being pulled by a rope. Okay, so it's going to be pulled forward, right, again. So what we're told is the case moves at a constant speed and there's a constant resistance to motion, okay? So the resistance to motion, the case is moving forward, right? Resistance, or sort of friction, is going to then go the other way like this. And I'm told that force is R, okay? I'm told that the case has moved a distance of 12. The work done is 96. Okay. And so therefore there would be a driving force moving forward, right? The forward force is a driving force. Okay. Or you might spot it's a rope. So specifically it's a tension force. But there we are. That's the setup here. Okay. Hopefully happy with that. There's a forward force that's pulling the case, and a resistance. So it's opposite to the movement. Okay. So it works backwards. Okay, I am told the case has moved a distance of 12 and the work done is 96. So we're told the work. Okay, so again, if we use the work formula, work is force times distance. Well, what force is it referring to here? So the work done is the force moving it forward, right? So it's going to be the work done for this force D, the driving force. So if we use the formula, then that's going to be equal to D times the distance, which I'm told is 12 meters. Okay. Well, I also know what the work is. It's 96. So actually, we just get this equation here. 96 is D times 12. Therefore, D, if I divide by 12, I get 8. So actually, my forward force is 8 newtons there. Okay. But they want me to find the resistance force R. Okay, so what do we do here? Okay, we don't know really anything about R, right? Now there's very specific detail here. they mention it's travelling at a constant speed. Okay, obviously we don't know what the speed is, but that doesn't matter. What you do need to know is constant speed whenever you see that term, specifically if it's constant, that means there's no acceleration. Okay, just something you need to know, which makes sense because acceleration is, it tells us if speed is changing. If the speed isn't changing, then there's no acceleration. But there we are. So that means we can mark it on as saying acceleration, right? Like this is 0. And that's going to be meters per second squared. Okay, we write it like this. Okay. So that means then, well, what else can we do? We can actually then resort to using F equals ma, forces mass times acceleration, right? Now, specifically, we're going to be looking horizontally, so right and left. Okay, so my forwards force is 8. Take away from the backwards force, which is R. That's going to equal the mass, and actually, we're not told the mass. We don't need it though, because mass times acceleration is 0. So actually it all just boils down to 0 anyway. Therefore, we can deduce R is 8. And that is my answer there. Okay. So hopefully that made sense. It's a bit different. It's a bit harder to the first one where we're just using the formula. Now we need to do some actual mechanics there. Okay. And drawing a diagram helps. Right. We've got this question now. We're told a parcel of mass 3 kilograms is pulled a distance of 4 meters across a rough horizontal floor. The parcel moves at constant speed. Again, what does that mean? No acceleration. The work done against friction is 30. Calculate the coefficient of friction between the parcel and the surface. So again, we've got this parcel, this little box that's moving on a floor. Okay, like this. Okay. So I'm going to draw my parcel. The mass is 3, so I'm going to say 3 kilograms. That's my mass. Okay. So, so it's being pulled. Okay. So there's going to be there's going to be some force forward, pulling it forward. But I also know there's friction. They mention friction is involved. So again, friction is the opposite. Okay, it opposes movement. It opposes motion. So it's going to go the other way. I don't know what the friction is. I'm going to call it F. I'm not told it, but what I am told is the work done against friction. Okay, so in other words, the work of the friction force. Okay. So the work of friction, well, again, that's force times distance. That's the work formula, right? So specifically, the force is friction. So that means F times the distance, which I'm told is 4 meters. So F times 4 is the work of the friction force. But of course, I'm told it's 30, the work. So that means 30 is F times 4. Therefore, my friction force divided by 4. I get 7.5, and so I can add that on to my diagram. Okay, but of course that's not what it asked me. It's asking me for the coefficient of friction. Okay, now the only formula that involves that is F equals mu R. Okay, so the friction is mu, the coefficient of friction. So friction is mu times reaction. So again, the reaction force acts here. I'll call that R. But then, of course, there's the weight force W, okay, as well. So those are my standard forces. So if I use this formula, then mu, if I divide by R, F is, mu is F divided by R. Of course, we know the friction is 7.5. But we need to find the reaction force. So how are we going to do that? Well, actually, firstly, we know that the weight, W, is mass times 9.8, or G, okay? But we take G to be 9.8, so G is an ongoing number, right? We know the mass is 3, so times that by 9.8. So therefore, W, the weight, is going to be 29.4 newtons. So we know that force. So now what we can do is look vertically to find the reaction force. So I'm going to say resolve up and down. So my up force is R. Take away the opposite down force of 29.4. And again, that's going to equal MA. So the overall force equals mass times acceleration. But of course, there's no vertical acceleration, okay, because it's moving forward. So there's no vertical acceleration, so it equals 0, okay. So therefore, R, the reaction force, is 29.4. So now we can work out what mu is, because now we know the reaction force. So 7.5 over 29.4. So that gives me mu, if I work that division out, I get 0.255 to 3 decimal places. And that is the coefficient of friction. Okay? Cool. Right. Okay, so we've got this example here. So here I'm told a sledge is pulled 15 meters across a smooth sheet of ice by a force of 27 newtons. The force is inclined at 25 degrees to the horizontal. By modelling the sledge as a particle, calculate the work done. Okay. Don't worry about this bit, about this particle stuff. If you haven't seen it, if you would have seen it in normal maths, it just means we can sort of apply the formulas nicely, essentially. But anyway, the main bulk, what's going on here is, again, we've got this sledge. So again, we've got this object on some sort of ice. So like this, I've got my sledge. It's being pulled 50 meters across by a force of 27. So you might think 27 forward like this. However, they've told us this force is 25 degrees to the horizontal. So what that means is actually at an angle. So instead of being completely flat like this, it's sort of at an angle like this. Okay. And so the angle is 25. So it's 25 degrees to sort of like the floor level there. Okay. Right, so what do we do here? Now you would, so it wants the work done, so we know that work is force times distance. You might think it's, well, the force is 27, so 27 times the distance, which we're told is 15 meters. Well, there we are. But that wouldn't be right. The force isn't just going to be 27 here. What we need to do, because it's at an angle, the way work works, right, the whole idea of the work is obviously the energy to move an object in a particular direction. Okay, so the sledge is moving straight ahead, straight forward. The problem is this force isn't straight ahead, it's at an angle. What we somehow need to do then is sort of find this sort of angle, this sort of line here, this sort of force here. Okay, that's straight ahead, right? That's straight ahead. That's in the direction where the box is moving, or the sledge, right? What we're going to do now, what we're going to do then is sort of call, is what we call putting a force into components. Okay, again, if you've done year 13 maths, you hopefully be familiar with it. But what we're going to do is say, well, actually, if I just draw out this this force 27 like this at an angle 25, what we're going to do is firstly go horizontally like this, so straight ahead. So if we start here and let's say we end here, first we're going to go straight ahead, then we're going to go straight up. Okay, so horizontally, then vertically up. Then you'll spot we get a right angle, and hopefully what you spot is if I get rid of this now and say that's 27, well, hopefully you spot we got a right angle triangle, right? And so we can use SOHCAHTOA. And so specifically, again, we want the forward force. So what side is this? Well, that's going to be the adjacent, right? So then if you remember your SOHCAHTOA, we know that cos 25 is then the adjacent, which is what we want, over the hypotenuse of 27. Therefore, the side we want is going to be 27 times cos 25. So if we work that out, that's going to be 24.47. Okay, so that is my force. That's the part of the force 27. This 24.47 is there. Okay, so that's 24.47. Okay, so that is specifically the part of the force that is straight ahead, that is horizontal, that's in the direction where it's moving. So that's important. The work, so the force, so the work has to be in this, the force has to be in the same direction of the movement. Okay, so it's moving forwards. So we want the forwards force. Okay, so this is the force we're going to use, this 24.47. So 24.47 times the distance of 15 gets the actual work we want to be 367.1 to 1 decimal place. And so there we are. Okay. Quite an interesting question there, but there we are. Okay, so now we're going to be looking at things moving up and down, so vertically, right? And so this will involve gravity, right? So I've got these two examples here. So firstly, we've got a parachutist obviously falling down. The weight force is pulling the parachute down, and then air resistance is acting up to oppose it, right? And then we've got this example here. So what's happening here is we've got a box being pulled up by some rope. Okay. Now it's hanging in the air. So again, there's weight that's pulling it down. So that's sort of the gravitational force, right? Weight is sort of gravity. So that's pulling the box down. Then you can sort of imagine then a person that's pulling up on the rope. And so that's pulling the box up. And now specifically, the force in the rope is tension. That's pulling the box up, okay? But that's the idea then, right? The weight is trying to pull the box down, but then the rope is pulling the box up. So in both of these cases, things are moving up and down. So the parachute is moving down, the box moving up, okay? Down and up, okay? So what we want to do here is actually we want to look at the work done, or the work of specifically gravity. Okay, now gravity, the force that sort of represents gravity is weight. Okay, now we've seen that in general work is force times distance. That's what we've used so far, right? For any force, the work of the force is force times distance. So the work of gravity, well, force times distance. But as I said, weight kind of represents gravity. So that's going to be weight of, so the weight is the force times distance, okay? Now, we know that weight is mass times G, okay? Now, G, remember, is usually 9.8. But actually, G is actually a large-ish sort of decimal, right? G is actually 9.80665. Now we don't tend to use all the decimals, so we just say that G is just 9.8. Okay, that's the background behind G. It's a number, it's a decimal, but we just say 9.8. Anyway, so weight is mass times this number G. Okay, so that means we can say that the work of gravity, well, weight, but we know weight is mass times G. So mass times G times the distance. Now, and so more, okay, and so we can be a bit more specific with distance as well. Now, if things are moving up and down, that's a height, okay? So the parachutist is travelling down, that's the height. The box moving up and down, that's also the height, okay? So specifically, how far up or down you move is the distance, is the distance here. So we can say that the distance is height. Okay, so height is vertical distance essentially. And there we are. That is literally my formula. So work done by gravity is mass times G times height. So how far up or down you move, like vertically up or down. And we can just say that if the mass is m, that's going to be m times G times height h. Okay, so this is the formula we're going to be using to work out the work done specifically from gravity. Okay, so the weight force. Okay, so there we are. Let's have a look at some examples. So here we're told a ball of mass 0.5 kilograms falls vertically 15 meters from rest. Calculate the work done by gravity. Okay, so we're going to be using the work by gravity, the formula mgh. Okay, now we know that the mass is 0.5. We're going to take G to be 9.8 and h, but the height is 15 meters down. So it's 15. Therefore, simply put that in a calculator. We get 73.5. And that being joules, right? And so there we are. Okay, now we've got this question. We're told a girl of mass 52 kilograms climbs a vertical cliff which is 46 meters high. Calculate the work done against gravity. So again, if I sort of draw a simple diagram here, so we've got this girl, the mass is 52 kilograms, and so she's climbing up, and so the height up is 46 meters. Okay, so the work against gravity, right? So in other words, the work of the gravity then, so the work done by gravity specifically, again, is mgh. We know that the mass is 52, G 9.8, and the height is 46. Okay. So therefore, work that out. We get 2344.1.6 joules. And there we are. Okay. Okay, so now we've got this question. We're told a bricklayer raises a load of bricks of total mass 30 at constant speed by attaching a cable to the bricks. Assuming the cable is vertical, calculate the work done when it's 7 meters. Okay, so again, the work done, right, it's a bit more vague, this one. So if I draw the situation here, so we have some bricks. Again, I'm going to draw it as a box, but this time it's moving up. Okay, so there's a cable that's pulling it up like this. So there's an upwards force. Okay. That's going to be a that's going to be specifically a tension force. Okay, if I'm being specific, because it's a cable, it's a type of rope. Okay, so the force in a cable or rope is a tension force. That's pulling it up. Okay, of course, then weight is going to go against it. And that's really everything. Okay, so again, it moves. We're told all the bricks here go up by 7 meters. So the height is 7 meters up. So hopefully happy with this diagram here. This is the situation. But they told us to calculate the work done when to calculate the work, right? Now, the work done, obviously that's going to be force times distance. In this case, the force is actually going to be the upwards tension force, because that's the force pulling it up. That's what we're interested in, the force that's pulling it up. And so the work of that, well, it's going to be tension times the distance of 7. Okay. So I just need to find the tension. How am I going to do that? How am I going to do that? Well, again, hopefully you paid attention. It mentions this key word, constant speed, which means there is no acceleration. So acceleration is 0. So it's moving up with 0 acceleration. So there we are. So no change in speed. So there we are. That's my acceleration, 0. Now again, I can look up and down, right? So if I resolve up and down here, well, my tension, take away my weight, is going to equal, well, mass, which is 30 kilograms, times 0 for acceleration. So actually just equals 0. So that means tension, the tension force equals the weight force. Okay. So we need to find the weight then. Of course, though, we know that weight is mass times g, or mass times 9.8. Okay, well, we know the mass is 30. So weight is 30 times 9.8. So that will get me 294 for the weight. Okay. And that being newtons. Therefore, my tension is going to equal 294 newtons as well. Okay. But they don't want the tension force, so the force upwards. They want me to find the work of the force. So now I can sub it into here to get the work to be 294 times 7. Actually, I'm going to do it down here. Work is tension times 7 for the distance. So that's 294 times 7. That'll get me the work to be 2058 joules. And there we are. That is the work done to move it up. Okay, so so it's the work to move the bricks upwards. In other words, the work done of the upwards force. Okay, so there we are. It's a bit tricky, that one. Okay. So we're going to look at a final set of problems, and so this one again we need some prior knowledge. Now we're going to be looking at problems where the floor isn't exactly flat. So in other words, like you can see on this table here, it's slanted, it's a slope, it's at an angle. We can see it's at an angle. If I was to draw a flat line like this, it's at an angle, say theta, right? But it's at an angle. Okay. So very simply then, again, the forces in this situation. So again, there's going to be a weight force that pulls the box down. Now, and then there's going to be a reaction force. Okay. Note the reaction force is at an angle. We'll go more about that in a second. Now, The box, obviously you can imagine it in real life. If you have sort of visualize it, the box is going to move down the table, right, because of the weight, right, the gravity. So again, friction will then act the other way to oppose it moving down the table. Okay, now I'm going to do a sort of example that's sort of based on this sort of diagram here. Okay, so again, I've got this surface now that's at an angle. So I'm going to draw a nice diagram, nice big diagram here. So you can see it's at an angle. If I draw a flat line, it's at an angle theta here. Okay. Okay. So this is my box. Okay, and again, the box is going to slide down the surface. So this is my surface, right? It's going to slide down, as you can see here. I'm going to say that the mass is going to be 5 kilograms. Okay, no, sorry, 10 kilograms. I'll say 10. Right. So if I now look at again this diagram, I went over here. Well, firstly, I've got a weight force that acts straight down. Okay. I have a reaction force that kind of acts up, but at an angle. So it's going to look a bit like this. That's my reaction force there. And then because the box is sliding down, then the friction is going to act up like this in the other way. Okay. So those are all my forces here. Okay. Okay, so hopefully with me here, right, that's just sort of the setup. Okay. Right, what I'm going to do now, well, firstly, if I just get rid of the box for a second, right, if I extend the reaction force down like this, actually, it turns out it's at a right angle. It's at 90 degrees to the surface, okay? That's going to be important in a moment. Okay. Now the weight. Okay, the weight. What we're going to do is kind of like one of the examples we've seen earlier in the video. I'm going to split. I'm going to do it in a different color. I'm going to split the weight up into two different sort of directions. So firstly, it's going to hang on, let me do it better. It's going to do this and then go here. So it's going to go down like this and then there. So instead of it going straight down, alternatively, I'm going to take this path. So this path here, then that path there, and then we end up here. Okay. So if we start and end, okay. So we can split up the weight into these two different sort of sides, okay? And again, we get, hopefully if I draw it out, if I draw this in yellow, hopefully you can see we get a triangle, okay? With here. And this is going to be a right angle as well, okay? So that's going to be not a right angle. Okay. Right. So I'm gonna so what also happens, if I can change the color, this angle here is, it turns out it is also theta. Okay. Why? Well, very quickly, again, if we consider this triangle here, well, we know that angle's theta, and actually, hopefully you can spot this is going to be 90 degrees. Therefore, because all three angles in a triangle have to be 180, right? 180 take away 90 take away theta gets me 90 minus theta. Okay, that's this angle here. Now, Get rid of this now. There we are. Now, hopefully then you can also see, if I do it in a different colour, that these two angles, 90 minus theta and theta, that actually is, again, a right angle. So actually these two angles have to add up to 90. Well, 90 minus theta add theta has to equal 90. So therefore this has to be theta, okay, as a result. And that will always be the same, okay? So when we set up these problems, this will be the angle theta here for this reason, okay? So there we are. So we end up, we can split up the weight. What we end up with, is the weight. And I'm sorry, what we end up with the weight is this triangle here. Again, I'll draw out the triangle. So this is that's my weight. And then I've got these two sides. I'll do it in red. We've got a right angle here and angle theta. Okay, now we can work out the weight as a number, right? We know that weight is mass times G. Okay. Okay, let me get rid of this. So we know that the mass is 10 and G is 9.8, so it's going to be 98 for the weight. So actually, the weight force is actually going to be 98, okay? So therefore, if I look at this triangle then, that means this side is 98. That's the hypotenuse, right? Because it's opposite the right angle. Therefore, we can come up with, if we focus on this triangle then, right, we can come up, using SOHCAHTOA, we can come up with expressions for the other, the red sides. So firstly, this side, that's going to be adjacent, right? So this is going to be 98 cos theta. And this side then is opposite, so it's going to be 98 sine theta. So we can add this on to our diagram, okay? 98 cos theta and 98 sine theta. So what we're doing here is essentially splitting up the weight into two different directions, okay? Hopefully you can see that right. That's the setup, okay? Right. So what we're going to do now is, we know what the weight is. I can now work out the reaction, okay? And I'm going to be using F equals ma, okay? I'm going to get rid of this now, this little triangle here. So that's the setup for the weight, okay? That will always work out the same sort of way, okay? Now, for the reaction, we're going to be using F equals ma. Now, previously, we have resolved or looked at either right and left or up and down, okay? The issue is this reaction force and the friction, they're at an angle. They're not completely flat, they're at an angle. So instead of looking up and down and right and left, and this is where the right angle stuff is important. We're going to be looking at resolving, firstly, along the surface. So you can see the arrows are slightly at an angle, right? So we're going to be looking at along the surface. So the forces along the surface, or the forces that are perpendicular to the surface. Okay, so firstly, if I look at the sorry, it will look more like this. So firstly, if I look at the perpendicular forces, okay, so what are my perpendicular forces? Well, the reaction force is perpendicular, so the reaction, and then hopefully you can spot if the reaction force is up like this, then this force, 98 cos theta, is going to be the other way, and it's going to again be perpendicular because that's 90 as well. Okay, so this 98 cos theta force is going to be the opposite to reaction, so take away 98 cos theta, and that's it. Okay, that's going to equal mass times acceleration. The mass is 10, and again there's no there's going to be no acceleration, okay, in this sort of direction. Okay, so no acceleration, so actually it ends up equaling 0. So the reaction is just 98 cos theta. Now I've not specified an angle here, so what I'm going to say is I'm going to take theta to be 30. Okay, so that means this angle here in the weight triangle is going to be 30 as well. So that means cos theta becomes cos 30. Okay, and so that means the reaction is 98 times cos 30 to be 84.87 newtons. Okay, so I can add that onto my diagram. Now friction's the only one left. Now if I tell you that the coefficient of friction here is 0.3, okay, we can now use the friction equals mu times reaction, or F equals mu R, to work out friction. So friction F is going to be 0.3 for the coefficient of friction times the reaction of 84.87. Okay, if I work that out, I get 25.46 newtons, and that is my friction. Okay, and there we are. Those are all my forces here. So that's if I add that on, my friction is 25.46 newtons. And so there we are, and that's generally the sort of setup, right? When now we're dealing with surfaces at an angle, okay? So there's an added complication with this sort of, when we split up the weight in this way, but it's the same thing every time, right? So we'll be doing this sort of thing. So that's just a simple example of how we do these sort of questions. Okay, now we're going to again go back to looking at work. Okay, and now again we're going to be looking at angled surfaces. Okay, so here we're told a rough surface is inclined at 40 degrees to the horizontal. A box of mass 1.5 kilograms pulled at a constant speed up the surface by force T, acting along the line of greatest slope. The coefficient of friction is 0.4. Calculate the work done by T when it moves 8 meters. Okay, so there's quite a lot of stuff going on. If I draw the situation then, again, a similar diagram to what I've just done. So firstly, again, we've got this surface that's 40 degrees. So it's going to look again something like this. Okay, so 40 degrees there. Okay, I have my box. The mass is 1.5. Okay. Okay, then we add on my forces. Well, firstly, I got my weight. Okay, my weight force, I'm going to call it W. I am going to have a reaction force, R. Again, that's going to be perpendicular. But, that's my reaction force acting up the box. Okay, then I know there's going to be friction. Okay, so the box isn't moving down. Okay, the box isn't moving down. It's being pulled up. Okay, the box is being pulled up the slope, so it's going to move up. So that means friction is going to act there instead. Okay, and we're also told it's being pulled up the slope by a force T. So now there's a force T pulling it up. So these are my forces. Okay. I'm told that the coefficient of friction, which is mu, is 0.4. And there we are. So we need to calculate the work done for T. Okay. So the work for T, so the work of the force T, again, that's going to be force times distance. Where the force is T and the distance we're told is 8. Okay. So we just need to find the force T. Okay, then we can find the work done. Okay, so what we're going to do here then, well, firstly, we can work out the weight. Okay, well, we know that the weight is mass times G, where the mass is 1.5, G is 9.8. So therefore, the weight is going to be 14.7. Okay. I can then work out the reaction force R. So again, if I now split up the weight, so this is what you want to be doing, split up the weight in this way. It will always be this way. Again, this angle will be 40. Then I've got 14.7, which is my weight, lots of cos 40, because again, this can be a right angle, and then 14.7 sine 40 there. Okay, that's my full setup. Okay, now I'm going to be looking at my forces. So firstly, if I resolve or look at the perpendicular force, so the perpendicular forces, so the forces acting in this direction. Okay, well, firstly, you can see the reaction force acts up like that. Take away then this 14.7 cos 40 force acting the other way. That's going to equal MA. Well, the mass is 1.5, but there's no acceleration. There's no acceleration acting up in that way. Okay. No acceleration acting upwards in that direction. Okay, so that means it goes to 0. So that means that equals 0. Therefore, the reaction force R is just 14.7 cos 40, and that equals 11.26 newtons. And there we are. Okay. Now we can actually work out the friction force because we know what mu is, right? So F equals mu R. So that means the friction force F is 0.4 times R. Therefore, friction is going to be 4.5. And there we are. Okay, and lastly then, we can now find the T force, right? So now, we're going to be looking at the forces that are along the surface. So the forces that are in this sort of direction, okay? Right. Okay, so firstly, we've got my T force. Then, obviously, then we've got this friction, this 4.5 acting the other way. Okay. But also, look at this. Look at this side, this little force here, that is also matching, or what we call parallel to the surface as well. Look at the friction force, right? Hopefully you can see that matches the direction of this 14.7 sine 40. So actually we're going to take away also, because it's in the opposite, of 14.7 sine 40, okay? Okay, and again, that's going to equal mass times acceleration. So 1.5 for the mass. However, as for acceleration, we're told it's again a constant speed. That means there is no acceleration moving up the surface. So zero acceleration. So again, that times by 0 to get us 0. Therefore, t is 4.5, add 14.7 sine 40. And so that gets me 13.95 newtons. Okay. There we are. Okay, so now that we know that the T force is 13.95. So now the work of the T force, by T times 8, because the distance is 8, that's going to equal 13.95 times 8. So therefore the work is going to be 111.59 joules. And there we are. That's the work of the T force. Right, okay, it's a lot there, but the steps are generally the same, right? But yeah, there we are. Right, we're going to be looking, we got this example. So here we're told a child of mass 25 kilograms glides 2 meters down a slope at 35 degrees. Calculate the work done by gravity. Okay, well, firstly, again, if we just sort of draw the situation, it's at 35 degrees now. Again, I've got my child. I'll draw it as a box of 25 kilograms. Okay. Okay, we're told the child slides 2 meters down the slope. So this distance travelled down is 2. Okay. Now, we don't actually need to add any forces on here because we want the work done by gravity. As we've seen previously, work by gravity is this formula, mgh. So the mass times g, which is 9.8, times the height. Okay, well, we know the mass is 25. G is 9.8. Now the height. Now height is vertical. So how high up or down we moved. This distance is not what we want. This is the distance down the slope. Okay. The height we want is sort of this length here. Okay. How are we going to work that out? Well, consider this triangle here then. So if we're moving 2 meters down the slope, so the slope here, 2, we've got an angle of 35. Okay. Now we want that height. Okay. When it's 2 meters on the slope, 2 meters. Okay. Again, we're going to resort to SOHCAHTOA because we've got a right angle triangle. So the height is going to be 2 lots of sine 35, okay? Because it's an opposite, okay? The height is the opposite here. So, if we do then 2 times sine 35, we get the height to be 1.147 meters, okay? So that's h for the height. 1.147, okay? So that is the height here, 1.147. So this height is how physically, how much downwards we've moved down. Okay. So The height is 1.147. Therefore, now I can work out the work done. 25 times 9.8 times the 1.147 to be 281. 0.05 joules. Okay, and that is my work there. Okay, right. Okay, we've got this question here, and now it kind of combines everything together, right? So here we're told a package of mass 2 kilograms is pulled at a constant speed up a rough plane, which is inclined at 30 degrees. The coefficient of friction is 0.35. The package is pulled 12 meters up the slope. Firstly, calculate the work done against gravity. Okay. So again, before I do anything, again, I'm just going to draw the situation. So again, we're at 30 degrees. Again, I've got my package. It's 2 kilograms. Right. I firstly want the work done against gravity. So again, that's going to be work by the gravity. It's going to be mgh. I know the mass is 2, g is 9.8. I need a height. I'm told the package is pulled up by 12 meters, so it's going to go up by 12 meters. Okay, but of course that's not the height. The height is here. So again, to work out the height, I'm going to do this little triangle here. Okay, so again, we're going to go 12 meters up. So 12, again, the angle's 30. So then the height here, then again, we've got a right angled triangle. We've got to use SOHCAHTOA. You can deduce the height. It's going to be 12 sine 30. So that will be 6. Okay, 6 meters. So the height is 6. So then the work by gravity is going to be 117.6 joules. Okay, then they're asking for the work done against friction. So now if we need to add on our forces, okay, I'm going to get rid of these lengths here. Okay, so I'm going to add my forces on now. So again, firstly, we have weight. Now actually we can be quite quick with weight, because we know that weight is mass times g, so it's going to be 2 times 9.8, and quickly we can work that out to be 19.6. okay, so 19.6. okay, then it's going to be a reaction force. Now it's moving up the plane, so if it's moving up, then friction's going to act there. Okay, it's going to act the opposite direction. Okay, so that's my friction force acting the other way, down the plane. Okay, I'm also told it's constant speed, so again that means no acceleration. So acceleration is 0 meters per second squared. So that is my setup. There's also going to be a force pulling it up, so I'm going to call that D for driving force. Again, driving force just means a forward force. Okay, so there we are. That's my full setup. Okay, so the work done against friction. So the work by the friction force, so again that's going to be F for the friction force times the distance. So the distance we're told is 12 meters. Okay, so remember, we're not interested in the height here, we're interested in the actual distance moved, which is just 12. Okay, we don't need to do anything special here. Okay, so we need to find F. Okay, how are we going to do that? Well, firstly, we can work out the reaction force. So again, if I split up the weight, again, I always want to split up the weight like this. So the angle here is 30. This is 19.6 cos 30 and 19.6 sine 30. Okay, so if I now look at the forces perpendicular, so in this direction, well, firstly, we've got the reaction force, okay? Then I'm going to take away, well, the opposite to the reaction is this here, this 19.6 cos 30. Okay. And so that's going to equal ma. Well, the acceleration 0, so mass times acceleration is 0. Okay. Therefore, r is equal to 19.6 cos 30. Okay. And so we can work that out as a number to be 16.97 newtons. There we are. That's my reaction. Uh, 16.97. Okay, but then I can work out the friction force, because I also know that the coefficient of friction is 0.35. This mu, right? I know that F equals mu R. Friction is mu times reaction. So that means F is 0.35 times 16.97 to be 5.94 newtons. So therefore, work for friction is going to be 5.94, because it's going to be force, which is my friction, 5.94 times a distance of 12, as we can see here. And so therefore, if we work that out, we get the work to be 71.29 joules. And that is my answer. That is the work done by the friction force. Okay, cool. Okay, so yeah, it kind of does everything there, that question. So make sure you understand this, the steps of that question. Okay, we're going to finish off with this question here. So here we're told, a rough plane surface is inclined at an angle alpha, sine alpha is 5/13. A packet of mass 8 kilograms is pulled at a constant speed up a slope. The coefficient of friction is 0.3. I'll make a note of that. Mu 0.3. Calculate the magnitude of the frictional force. So it's asking for the friction, basically. So again, if I draw the situation here, okay, so it's angled at an angle alpha. Okay, they've not told us what alpha is specifically, which adds a little bit of complexity. But that's the angle. Okay. And so then I have my packet. Again, I'm going to draw a box. The mass is 8. Okay. And so my forces, well, firstly, again, I've got my weight. My weight is going to be mass times G. So that's going to be 8 times 9.8. And so that will be 78.4. Okay. And so then I can split up my weight in this way. So this is also angle alpha. This is going to be 78.4 cos alpha and 78.4 sine alpha. Okay. Then I've got my reaction R. Now it's moving up the plane. Okay. So it's going to move up the slope. So that means the friction force is going to act that way down it, the opposite way. And so it's being pulled up. So again, there's going to be a driving force pulling it up in this way. Okay. So there's a force pulling it up and then the friction acting the opposite way. Okay, those are all my forces. Now the acceleration, again, it's constant speed. So once again, that means the acceleration is 0. Okay. And that's everything. I think that's everything. So we need to work out the friction force. Okay. Right. Well. We know what the mu is, right? The coefficient of friction. So that tells me we're going to need to use F equals mu r. Okay. So F then is going to be mu, which is 0.35 times the reaction force. 0.3 times reaction force. So we need to find the reaction force, okay, in order to find F. So what I'm going to do then is I'm going to look at resolving perpendicular, so in this sort of direction, okay. So firstly, I've got my reaction force. Then I'm going to take away. The opposite to reaction is this 78.4 cos theta. Again, hopefully it's the exact same sort of situation every time, right? So then that equals ma, where there is no acceleration in that sort of direction, okay? The acceleration acts in that direction. There's no acceleration there. So that means it equals 0, and so therefore r is equal to 78.4 cos alpha. Now, this is where it throws a bit of a spanner in the works, because we don't know what alpha is specifically, okay? What we do know about alpha is what sine alpha is. We know sine alpha is 5/13. Now, we want to find cos alpha. What's cos alpha? Okay, again, we need cos alpha here. Now, you might think, well, let's just do inverse sine, right? So if we did inverse sine of this, the issue is you'd get a nasty number, 22.619 blah 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 degrees. If we then did cos of that, well, sometimes it might work. Sometimes, would it work here? It does work here. Okay, spoiler alert, it's 12/13. But you can't rely on that, and that's not what we call like a formal method to get the number, because it turns out cos alpha is an exact number. As we've seen, it's 12/13. A trick we can do, and actually you probably find it's more efficient once you really master it. What we can do instead is use sine alpha and use SOHCAHTOA, okay, from GCSE, okay. So if I construct a triangle, again with the angle alpha. Now, so I know that sine is opposite over adjacent, right? Over hypotenuse. Okay, if I literally compare the fraction, then the top number is the opposite. So this number, this side is 5, and so the hypotenuse here is 13. If I now do some Pythagoras, I can work out this adjacent, right? So that's going to be, the adjacent is going to be the root of 13 squared take away 5 squared. That's going to get me 12. Okay. So there we are. So hopefully happy with how we got to this triangle here. Okay. This triangle here. Okay, so I literally just use the sine alpha they've given me, and then the 5 is the opposite and the 13 is the hypotenuse. Then I worked out the missing side, 12. Okay, doing some Pythagoras. Okay, now I can use this to work out cos quite easily, because now again cos is adjacent over hypotenuse, so that means cos alpha, the adjacent is 12, hypotenuse is 13. And that is my answer for cos. So actually doing it this way gives me a sort of way to work out cos from sine without having to find alpha on its own. Because alpha might be a really awkward number, and sometimes you might not get the exact fraction. Whereas this method you do. Okay, it's a more proper method, this is. But there we are. That's cos alpha 12 over 13. So now I can say R is 78.4 times 12 over 13. Then I can put that in my calculator. And that will get me 72.37 there. Okay. Right. So now I know what R is, I can find F. So now friction, F is 0.3 times 72.37. So that will be 21.71 newtons. And that is my friction. 21.71. Okay. And my reaction was, what was it? 72.31, 37. Oh. Okay. So that's part A. That's the friction force. Okay. Then they told me the packet moves 15 meters up the plane. Okay. So firstly, they want me to find the work done against friction. So the work done against friction, or the work. So the work by the friction, right? Work by friction. Well, that's the friction force, which is 21.71 times the distance moved, which we're told is 15, right? We're told it's 15. Okay. So we work all that out. We get 325.66 joules. And that is the work done very simply. Okay. And again, this stems from force times distance equals work. Okay. That's the formula I used here. Okay. Then for part C, they now want me to find the work against gravity. So now remember, that's the formula. Work by gravity. That's mgh. So the mass is 8. G is 9.8, and the height. Okay, well, again, if I draw the situation, I've got my angle alpha. I'm told the distance is 15 meters up the plane. So 15 meters along the plane, along the slope, 15 meters there. So my height h is there. So now, by SOHCAHTOA, h is 15 sine alpha. Now we know what sine alpha is, right? Sine alpha, we're told, is 5 over 13. Now, simply the height travelled is 15 times 5 over 13. And so that will get me the height, the vertical height, to be 5.77 meters. Okay. So that means my height is 5.77. So that's how high up vertically you travelled. So therefore the work by gravity, if I do 8 times 9.8 times my answer, 452.31 joules. And that is the work done by gravity. Okay. And so there we are. So there we are. So that's looking at work done. So hopefully these examples have helped, and also the recaps have helped. If you're really sharp from normal maths, hopefully it hasn't been too dragging. Hopefully it's not been too taxing. But yeah, I thought you needed I thought it would help to go over the prior knowledge, just so everyone's up to speed as you look at these questions. Okay. So there we are. That's work done. No pun intended, but I'll see you next time.